Welcome back, students, and with this video we will start our tutorial working with interpolation and geostatistics. So at first open the document, tutorial 9, Word document, interpolation and geostatistics, and also open the ArcMap document, interpolation and geostatistics, and in case if the link is broken, please repair the link using the repair data source. You can also use the properties and go to set data source. We will work with two types of vector datasets in this model: elevation points, point observations of the certain region, and the region, the vector shapefile. And let's start our tutorial. So activate the geostatistical analysis tools package. When it is activated, it can be seen in a menu box. Let's first activate it. So we can do it, or we can just click with the right button to the menu box and activate geostatistical analysis. Here it is. Here it's activated. We can use the snipping tool to show that it's activated, right? So we can just focus. Today, by the way, the first part we will work with the deterministic methods of geostatistics. At first, let's open the geostatistical wizard within the geostatistical analysis tools. So here is we can open it with this tool, or we can go to the scroll button and get geostatistical wizards. So here you can see the deterministic methods, right? Actually the four types of interpolations in the IDW: global polynomial, radial basis function, and local polynomial. So open the geostatistical wizard. So we opened, click to IDW method, and for elevation for a source dataset, and data field for source dataset and data field, and that's it. And for data field, choose height attribute and move to the next step, clicking next button. So here we can choose the inverse distance method. For source dataset, we will use the elevation points, and for data field we will use the attribute height, which contains the height measurements of the our region. So let's make a print screen here and put it here, and for using the Ctrl V, the next button, right, we'll go to the next step. So here it shows the semi-virogram of our interpolation. I will not focus here on the just statistical concepts. General properties: inverse distance method, inverse distance weight interpolation explicitly makes the assumption that things that are close to another are more alike than that are farther apart. To predict value for any unmeasured location, IDW uses a measured value surrounding the prediction location. The measured values closest to the predicted location have more influence on the predicted value than those farther away. IDW assumes that each measured point has a local influence that diminishes with distance. It gives greater weights to points closest to the prediction location, and the weights diminish as a function of distance. Hence, the name inverse distance weighted. Weights assigned to data points are illustrated in the following example. So here we can see the weights, which here just sorry. Here we can see the red dots, right? Samples which has the higher influence. Here's the weight, 26, right, and almost 27%. 3 dots, and these points have the smaller weights. In our case, for instance, this these points has the biggest weight, this has the smaller weight, and this has even more smaller weight. The weights window contains a list of weights assigned to each data point that is used to generate the predicted value at the location marked by the crosshair. Here is the center crosshair, and the center of this cell will gain the certain value according to the influence of these points. Can just so just short information when to use IDW. A surface calculated using IDW depends on the selection of a power value and the search neighborhood strategy. IDW is an exact interpolator where the maximum and minimum values in the interpolated surface can only occur at sample points. The output surface is sensitive to clustering and the presence of outliers. IDW assumes that the phenomenon being modeled is driven by a local variation which can be captured by defining an adequate search neighborhood. Since IDW does not provide prediction standard error, justifying the use of this model may be problematic. So the search, we can also talk about this on the next slides. So neighborhood type standard, we can just make change it to smooth, but let's keep it standard. Maximum neighbors, we can also change it to just 10, right? Maximum minimum neighbors, probably for instance 5. See, the output is changing, and now here is 4 sectors, or with 45 degrees. So we'll just sorry. So here are the weights, which are the influence of our weights. See that a lot of points, 40 neighbors, influence to our output pixel. When we choose sector type, it changes. I prefer to use 4 sectors. So allows a choice of 1, 4, 4 with an offset of sectors. So just short information about the sectors. Once a neighborhood shape has been specified, you can restrict which data locations within the shape should be used. You can define the maximum and minimum number of locations to use, and you can divide the neighborhood into sectors. If you divide the neighborhood into sectors, the maximum and minimum constraints will be applied to each sector. There are several different sectors that can be used and are displayed below. The points highlighted in the data view show the location and the weights that will be used for the predicting a location at the center of the ellipse. The search neighborhood is limited to the interior of the ellipse. In the example shown below, the 2 red points will be given weights of more than 10%. In the eastern sector, 1 point will be given a weight between 5% and 10%. So, okay, let's just choose 4 sectors. Click next. So it also, you can save this statistical information about major semi-axis, minor semi-axis, sector type, neighbor of to include at least, and power. I prefer not to save it. So here is our inverse distance method. Here is our result. We can just close this and represent this, snip this map and put it to our file. So we finished our interpolation, but it looks not like we wanted. But the question is, what is the data type of your output? We can check it. We can probably see that this is a raster map, but we can see that it doesn't contain the attribute table. Also, so when we go to source, we can see the data type is shapefile feature class. But if it's shapefile feature class, why it doesn't contain the attribute table? Actually, it's the input data type is shapefile feature class, geometry type is point, so we're talking from about this. Count of points is 100, data field is 8. So also information about the coordinate system, and in general, so it doesn't show the actually the data type of our output dataset. Even this dataset doesn't have the reference, so it's not stored in our local disk, so it's temporal data, and we should make it a constant dataset. So however, we can see that the map doesn't fit our boundaries. Here is our boundaries, right, of our map, of our region. Open layer properties and go to extend. Set the extend to region shapefile. So okay, let's go to layer properties. It's just a temporal layer, and we should open the extend. Set the current extend to the region. Okay, we just can make a snip. So we put the rectangle extend to region. So extend has changed to region, but we also should change the mask to set the boundaries of the region shapefile. Go to data frame properties and open data frame panel. In clip options, choose clip to shape. Okay, now we go to data frame properties and we go to data frame. Here we can see the clip options, right? We choose clip to shape and open specified shape, and here we choose outline features. We'll make a print screen here. Here is our region, right? I made a print screen. Okay, and now we can see that our our interpolation took its final form, but it's not a constant data set which is stored within our our local disk. So in order to save our results, we should save it either as a vector file or raster file. Mostly we use the raster as for interpolation. So your interpolation is a temporal layer which is not saved in your local disk. Right click mouse button and save it as a raster file with pixel resolution 30 meters. So we go to our layer, right click and go to data and export to raster. So inverse distance weight method, and I go to my file workspace. You can save it in your file, and just called IDW, right? Save, give a name, and the pixel resolution is 30 meters. And number of points in the cell, or it's optional, you don't have to save it. So okay, I click OK, and now it's exporting my ArcMap. So it will take some time to export your layer, geostatistical layer, to the separate raster dataset. So here is our output, right? You can see it. Oh. You know, when you just export to raster, right, it's better sometimes to use the cell size, which gives you the ArcMap automatically. So sometimes mostly it concerns you when you have the slow computer capacity. So actually I will write here or done by ArcMap automatically. So in this case actually I used the original raster cell size used given by ArcMap automatically. So here is our IDW. It's continuous raster, so it doesn't have so far the attribute table because we should convert it to the discrete raster. So follow the same steps with the deterministic methods, and display results with the final maps. So let's just first I will put the numbers of minimum, maximum, and root mean and root mean square error by IDW. So the minimum value here we can find the statistics, right? Minimum is 151, maximum is 1495, mean is 768, and the standard deviation, the root mean square we actually can find in the this place. So root mean square error, here you can see the standard error of the interpolation, so it's huge here if you're familiar with the statistics. So here is our root mean square. And let's compare also the other methods, right? So I will pause the video here to follow the same steps and try to fill this table. So I just finished my analysis, and here I have the 4 interpolation methods as raster datasets. I can group them. And also here are the geostatistical layers from the geostatistical analysis. Just here is continuous rasters, right? Okay, and here is my table is filled. You can see that there are very huge discrepancies between the minimum, maximum, and medium. So the mean is the same, but minimum and max of the pixel values, in our case elevations, are different in output datasets. And the Ramassier root mean square is also has some differences. These are the results. So we can see here that they can really differ. And by the way, while just also if you want to know more about the types of the methods of working interpolation, just go here to geostatistical wizard, and I ask you to read more information with the ArcGIS help. You can see there is plenty of information about each geostatistical tool. And while exporting raster, just try to not to change the output cell size, because here I can write this value can be explicitly set on the raster analysis from the environmental settings. If it's not set, it is the shorter of the width or the height of the extent of the input point features in the input spatial reference divided by 250. Okay, so this is the end of the first part of our tutorial 9, and let's go to the second part, where we will use various types of kriging method.